So hi, I'm Rafi. I'm from Refael. And today's talk is about end-to-end reinforcement learning-based system for autonomous driving in unapproachable environments. So end-to-end means we only give an image and the agent drives. Reinforcement learning means we don't give him any supervision. It tackles obstacles and learns not to do it. And unapproachable environments is places we can't train before we reach them. So what is reinforcement learning? It's learning from self-experience. There was a very good tutorial today about it. We have an agent which constantly interacts with the environment. The environment gives the agent a state. The agent takes the states and decides for an action. And the environment given a reward for this action. Reinforcement learning can learn when the game rules are unknown, when the rewards are delayed, when there is no supervision but self-supervision, and even if the action affects the environments. In recent years there have been many successes. Some researchers got superhuman performance in many games like chess, Go, Atari games, in some control problems, etc. So our mission is to teach a vehicle to drive in a specific off-road area. We're off-road, this means we don't have roads, we don't have traffic rules or anything to help us. We only have obstacles and we don't want to collide with them, and we want to reach a certain point in this field. We test and train the agent in the same place. This means we don't teach the agent to drive. I teach it to drive over here. So if I put it in somewhere else, I don't expect it to do very well. I want him to be able to drive in a very specific area. Now I can't use supervised learning because it requires large annotated data sets, and I don't want to annotate data sets. It's boring. I can't use physical reinforcement learning because I will first, it's too slow. I need millions of iterations. It will take me years, and it's very unsafe. There are people living there. So our solution is to copy-paste the environment into the computer. I mean to do realistic 3D modeling of this environment, but I do it only using aerial images. So I don't have to be there. I only need someone to take a picture from a plane, and I can do a 3D modeling, and I can train the agent inside the model in such a way that when he goes there, he can drive safely. So I do reinforcement learning training inside the model, and as a bonus, in this way we can drive in currently unapproachable areas. So I can learn how to drive on Mars just from aerial images from satellites of Mars, and when I'll get to Mars, I'll know how to drive there. This is not what we're doing today, yes? We're not driving on Mars. So the main novelty of this work is splitting between two missions. The main challenge is driving involves two tasks: navigation and avoidance. Now they are both mixed. They both affect the location and the pose of the vehicle. However, they are very different. Navigation or path planning is a strategical task. It has sparse rewards. You only get a reward when you get to the target, and it has geometric input. You only know the location of the vehicle now and the target location. Obstacle avoidance, on the other hand, is a tactical task. It has dense rewards. For each step you know if you collide into an obstacle or not, and it has a visual input, usually an image or a depth map or a obstacle map if you're lucky, but that's it. Now, doing both together is hard, and so we split them. So we have a navigation system. This can happen even before the mission. We have the current location and the target location, and there's a navigation system which gives us a track, which never mind. And then we have an avoidance system which happens during the mission. There's a rendered image, and the reinforcement learning agent takes the image, makes a driving decision, he drives according to this, reach a new location, a new image, and so on. So we'll start with the navigation system. Like we said, we can do it before the mission. We have a 3D model, we extract the geometry, And then we do segmentation by possibility. The yellow area is everywhere the vehicle can go. Then we do watershed algorithm to extract the trails and the width of the trails. And they are color coded. The redder are the wider trails. We can remove narrow trails according to the actual vehicle width. We can do Dijkstra algorithm to extract the shortest path to the target. And finally, we can summarize the track into a list of waypoints, just like Waze, that tells you in 100 meters, turn left. So this is the output of the navigation system. When we come to avoidance, we have to deal with two different vehicles, drones and cars. Drones are a bit simpler. They can rotate in place. They can move in one direction while steering to another direction. Car cannot do it. It can only turn while moving, and it moves only to the steering direction. So we have two different algorithms for both vehicles. Let's start with the drone. It's simpler. So in each driving step, the model is rendered to the agent location. Now the way we tell the avoidance system about the navigation order is that the next we steer it to the next waypoint. That way the agent uses the rendered image to avoid obstacles, while unknowingly progress toward the target. So if it decided to go straight, it goes toward the next waypoint and finally to the target. But if it has an obstacle, it can avoid it using left or right. So we wrap the driving simulator with a game. We gave scores, negative scores for crashing, positive scores for arriving, and we trained a reinforcement learning agent. Now the car. The car is harder. We said that it can only move to the steering direction. So we can't give the navigation orders using the steering. We cannot point the drone like we did to the drone. We pointed that to the next waypoint. We cannot do it to a car. If it wants to avoid an obstacle, it has to steer to another direction. Also, small avoiding maneuvers can cause losing the next waypoint. Like it has a parking car, it goes right, and now it is in a different street, and it cannot go back to its track. If that's happened, the rest of the navigation orders will be misleading because I'm in the wrong street. So we have a slightly different navigation system. We program a phantom car which drives ahead of the car using only a map and a track, and it's ignoring obstacles because it only has the map. So this phantom car is driving in front of me, and the phantom car can recalculate the track online. If I got into the wrong street, the phantom car can understand that and recalculate a new track. And this way I can avoid the misleading navigation. Now the navigation recommendation, like we said, we cannot give it using the steering, so we just give an arrow, the little arrow up in the top of the image, embedded into the image. Now the agent see both things. It can see the arrow, the navigation order, and it can see the image. And it can choose if to navigate using the navigation order or to avoid the obstacles using the image. So the training, we trained using three state-of-the-art actor-critic-based reinforcement learning algorithm, PPO, A2C, and actor. The network is built such that we share the convolutional layer between the actor and the critic. The joint network learns an image representation, and the actor and the critic are both only one fully connected layer. So the actor gives an action, and the critic gives a grade to the action, and then the actor trains according to the grade the critic gave him. Some other details: we used the random track in every game. We added random obstacles and in every game, and we use multi-process, about 8 processes, and only one training agent using all those games. The car training did not go well, so we had to add some steps. The first step is only a black image with the arrow on top, only to teach the agent to obey the navigation orders if there is no obstacle. Then we add a middle step that it should do exactly the same while there is an image in the bottom. And finally, the car starts moving, and it has both to obey the navigation and avoid obstacles. Some training results. So we have here the three algorithms. We can see that actor failed to train. We can see the cyan line, the human mean performance. This is not world champions or something. It's just two gamers. One of them was me, playing for 1 hour. Like you see, the humans are not doing very well. This is not their fault. My fault. It is my fault. This is not a good game. This is a very hard game to drive in. However, we can see that both PPO and A2C managed to reach superhuman performance very quickly. If we smooth it a little, we can see that even though A2C is much more volatile in its progress, however, it outperforms PPO and reach better a better agent much quicker. So this is the results of the drone. We can see it inside you can see the 3D model, the realistic 3D model. This is an IDF training facility. You can see right now that it can move to the right while steering to straight. When it reached a waypoint, you can see it rotating in place. And finally, it will reach the target eventually. Now, some of the obstacles are constant, like the houses. Some of the obstacles, like this, are things we added only on this run. Now, the car results. I'm sorry for it. It is much slower. You can see the arrow at the top, the navigation order. You can see the car can only steer while moving. Here it has a much harder track inside the small trails of the village. And when it says success, it means it reached the final target. Okay, so future work. We have much work in the future. First, we want to integrate moving obstacles. This is much harder than urban driving because the other cars or vehicles are not obeying any traffic rules. So we will have to prepare for anything they can do. It's an open area. The next thing we want to do, we want to use GANs to do the rendered images much more realistic. So first, we want it to be just look alike the actual reality now. And I know the rendered images were realistic, but they are not similar to what the robot will see when it will reach the field. We can see in the top image how this place looks right now. We want to address rain, mud, darkness, fog, dust, everything that can interfere with the image. You can see in the second image that even a little rain can make the whole ground much muddy, and the robot can be confused only by this. Finally, we want to do control learning. Like you saw, the drive-in actions are very simple. It's only as straight or turn 3 degrees to the right or 3 degrees to the left. This is not how a real car operates. And even if we trained on a real car model, The actual robot will have a different control, a different delay between the action and when it happens. Steering of one angle makes the actual steering of 1.5 angles, and so on. So we want to take the actual robot, drive with it, learn it control parameters, and then retrain the reinforcement learning agent using those control parameters, so it will learn how to drive this robot in this environment. And like I said, we want to drive a real platform like this little robot in the image, and we will test it in this place. We chose an IDF facility so we can be sure there is no human during the test of this real robot. Thank you very much. If any questions, yes. Well, first it didn't work. that's the, that's the first thing I tried. Also, many others hints didn't work, like different locations to tell him like a constant arrow to tell him where is the steering direction, the target direction. What I think is that convolutional neural network is very good at spotting a pattern, and left and right arrows are very distinctable pattern. This is why I chose it, and it worked.